welcome to the lecture of this finite volume method. Now we can actually approximate how many number of points you can have, and so for example, let us say you get this particular C element and you have the faces 1, 2, 3, 4, 5, 6, this is the centroid of that element, and your neighboring F1. To get this flux integration, I have one integration point. So, as I have mentioned that IP refers to the integration points and IPF is the number of integration points along the surface F. So, this is a particular surface, let us say, which is connected with F1 and I have one integration points. So, that means in this case IP is 1 and also WIP would be 1. So, I get a nice calculation for the flux calculations. Now, one can have multiple integration points. If you have multiple integration points, then what happens? Let us say you have two integration points along the surfaces. Okay. So, every connecting surface will have two integration points 1 and 2. So, in this case IP is 2. So, if IP is 2, now my weighting functions are going to be different and then I can get two different numbers xi1 and xi2. These are the and weighting function W1 equals to W2 equals to half. So, the previous case I had one integration point, so W1 was 1. Now, this case I have two integration points, so the weighting function would be half and half, and this xi1 and xi2 dictate the distance from one particular point to F1 and then other side F2. So, they are the distance. Similarly, you can have 3 integration points. So, that case my IP would be 3. So, if you have 3 integration points, IP would be 3, then obviously my weighting function W1 would be 5 by 18, W2 would be 4 by 9, W3 is again 5 by 18. So, if you look at that weighting function, they are equally sort of distributed. Then the distances would be xi1 is 5 minus root 15 divided by 10, xi2 is half and xi3 is 5 plus root 15 divided by 10. So, these are the distance from one point to the other points. Okay. So, essentially what I got is that rho v phi dot dx, it get me back this summation of F, this is faces over V. So, IP over IPF WIP rho v p IP dot SF. So, that is what you get, and similarly for gamma del phi dot ds, that is my diffusive term. So, you get F faces over V and IP over F WIP minus gamma del phi IP dot SF. So, this is what you end up getting, and okay, and the source term you can always calculate by doing the integration like the source term you can always get q dv equals to summation of ip over v q ip w ip v. So, that is the way you get the source term integrated. So, then you can, and IP and all these will depend how many integration points you have over the surface. Okay. Now, you can get the similarly the volume integration points with one integration point. So, basically the volume integration of source term. Similarly, you can have one point, you can essentially one point means here you could have 4 integration points. Now, other case you had the points along the surface. Now, when you try to get the volume integration, you need multiple points inside the element of the volume. So, you could have 1 point to integrate, you could have 4 point to integrate. Okay. So, or you can have more. So, if you have it, then accordingly your calculation of this xi and WIP, they will be different. So, and you can also, I think you can have the 9 integration points. So, it depends. So, all these points, so IP can actually vary, accordingly your WIP will also vary. And so, your integration that you have got here, like for the source term, that q dv, this is your volume integration of that. So, that will have the IPV, QIP, WIP, V. So, this actually represents that how many points I have inside that volume, and that is why this loop goes from number of points inside the volume. So, the difference remains between the flux and the volume is that in the flux calculation the number of points they are varied along the faces. When you come down to the source term integration, which is a volume integration, the number of points vary within the cell. Okay. So, after getting all these done, if you look at that particular element C and you have all these neighboring elements and they are connected with the faces. So, my transformed equation become obviously over element C, that would become like F NB of C rho V phi minus gamma del phi dot SF equals to Q dot Q C B C. Okay. So, that is my transform equation. So, what I started off a differential equation of steady state equation of the scalar transport equation. Now, I have written algebraic system. This is nothing but the integration over the faces, because these are the fluxes. So, that means it will go from 1, 2, 3, 4, 5, 6. So, all these fluxes to be integrated. Now, another thing that one may wish to do is the linearization. Okay. So, you can linearize the system, and so how do you linearize the fluxes? You had this total flux JF dot SF. So, you can actually you can say this is the total flux TF, that is total flux, and that can be realized as the flux Cf plus flux Ff plus flux Vf. What do they stand for? So, this essentially means my total flux for phase F. If I consider F1, then my total flux would be, this is essentially my Jf phi, that includes both the component. Okay. So, that has both convection and diffusion. So, this represents total flux. What is this? Thus, this term actually represent the flux linearization coefficient for element C. That means, this is the element which I am interested in and trying to get the equation integrated over that. So, when I do the linearization, because this is the total flux along this phase and this phase is connected with phase F1. So, one contribution comes from the linearization coefficient of this particular element along this phase. So, the second is that flux linearization coefficient for F, or you can put element F, for element F. So, if you are talking about this flux, so mind it that we are talking about total flux for a particular phase. So, the total flux linearization at F1 must be different from F2, but if you look at only one particular phase, again if you look at this equation where you have the total system which is integrated to the algebraic system, you have a loop over all the phases around that particular element. For this particular example, you have to have this loop go over from 1 to 6, because you have 6 phases. Now, once you go down or come down to each of these phases, now if you can look at each fluxes. So, along one particular phase, it needs to be linearized between this element and this element. So, one coefficient come from this, another coefficient come from element F, and then you have a component which is called the non-linearized part. Okay. So, you get 3 component. Okay. So, the total flux along a particular phase is decomposed in essentially 3 components. One component come from the element itself, the coefficient of the linearization. Second component come from the linearization coefficient of the neighboring or the connecting cell along that phase, and third coefficient is the nonlinear part. So, if you look at all these 6 phases, you will have these components. Okay. Now, if I essentially write down that equation which is going for this element dot SF. Okay. So, this would be nothing but my F, the total flux. Okay. So, that means this equation, left hand side of the equation I am writing it is the total flux. So, this nothing but the F over that element, you have flux Cf phi c plus flux Ff phi f plus flux Vf. That means, if I come down to phase 1, this would be flux C1, I mean the coefficient of C1 phi c, coefficient of F1 phi f, flux V1. Okay. So, for all the phases you can write down, and then I have the source term QC and Vc equals to essentially the total flux. Okay. So, if you write down the flux C phi c, the flux F phi f. So, it is a linearized equation. Okay. Now, if you have let us say constant source term, what happen? The constant source term. So, I am again writing the source term in this kind of fashion, the contribution coming from the C element, contribution coming from the neighboring element. Constant source term means flux C would be 0. So, sorry, this would be this is flux V. So, my QC Vc is equal to flux V only. Okay. Now, if you substitute everything back in this particular equation, okay, if you substitute everything back there, you get phi c AC plus summation of this integration AF phi f equals to BC. So, essentially this expression and this expression, both of them are, if you collect them together, you get this. And what AC stands here? AC is F NBC flux Cf minus flux C, and AF would be flux FF, and so BC is nothing but summation of F over this element flux Vf plus flux P. So, what you have here and here, if you put them together, then you get this. So, this is nothing but your linear system, and if you put them in a matrix form, this is going to get you back the X equals to B. Okay. So, the thing is that over a particular element C, you integrate your equation. So, the integral equation will look like that, and once you compute all the fluxes and put them together, so you get back this system. Now, here you get a linear system like this. You cannot solve without having the, so once you need to solve this linear system, the important ingredients are to have the boundary condition. Okay. One is the boundary condition which will fit to this system, and then the linear solver. Here you can have direct solver, you can have iterative solver. Okay. So, we have already discussed in a, I mean very quickly what kind of solvers, but in details we will do later on in a due course of time. But now let us look at the boundary condition, how do you implement that. So, first one important condition is that you have the value is specified. That means, in other words, you say it is a Dirichlet boundary condition. Okay. So, if you have a cell like this, what you had, like okay, and then you have a point here. Now, this is your C center, and this is connecting, and this would be the normal. Okay. And this is where your phi b, this is the boundary surface, this is T, this is specified. Okay. This is the point B, and this is E b. Okay. So, if phi b is specified, then I should have phi b equals to phi b specified. Okay. Then at that particular phase, this is the boundary phase, this is the boundary phase, my JB phi dot SB, this is the, if you look at this integration. So, at that particular phase, this will become JB phi dot SB. So, which would be, if you just say the convective part, rho V phi B dot, so this is flux C B phi C plus flux V B. So, this will get you back rho B V B dot S B phi B, which is nothing but m dot F phi B specified. So, you can have flux C B is 0 and flux V B is m dot F phi B specified. So, you get that value. So, once you have that value, then now the second type of boundary condition would be specified flux. Okay. That means called the Neumann boundary condition. So, if you look at the same element here, this is the center, then you come, this is the normal, this is E B, this is point B, this is T, this is where Q B specified. Okay. So, once you do that, then your JB phi dot SB would be JB phi dot NB SB. Okay. So, this is your specified flux. So, which is nothing but QB specified SB. Okay. So, my flux CB is 0 and flux VB equals to QB specified SB. So, these are the two type of conditions that you can specify at the phase. So, now we will continue from here in the next lecture. Thank you.